Hello, everyone. I'm Dan Bossi, and I'm pleased to have you for I think, a very dynamic seminar and webinar due to Dr. Olivia Kellner. Olivia spoke at our GrainCom conference last year in Geneva, Switzerland, and did just an outstanding job. And so since that conference, there's been an awful lot of buzz in the world about AI. And so we're actually having a segment at GrainCom in terms of AI and how it'll affect farmers markets and a lot of other things throughout our industry. Here today, Olivia or Dr. Kellner is here to talk to us about the opportunities that AI present in weather and how it'll impact forecasting. Now, again, this is a really important growing season for much of the world. The US, Black Sea, much of Europe has been experiencing varying degrees of extreme wetness or dryness. And so as we head into this new growing season, the importance of all this will determine whether we have markets that are sustaining to the upside, or maybe we still stay in the bearish trend that we've been at. So I think supply or Mother Nature is so key going forward. So with that, I'm excited to introduce you to Dr. Kellner. I find her as one of the best forecasters and climate analysis folk in the business. She works with Scott Eucness at Climate Impact Company. So Olivia or Dr. Kellner, take us forward in understanding AI and weather and what you all think in terms of the opportunity. I turned it over to you.
All right, thanks, Dan. Thanks for that introduction. And thank you for having me today. This is definitely an exciting emerging topic to talk about within the weather industry and with applications obviously far-reaching across other industries as well. So in my presentation today, I'm going to present to you just a high-level overview of artificial intelligence and weather forecasting. And to do that, I'm going to present the fundamental basics. So how numerical weather prediction works today, and then how artificial intelligence works now with weather forecast models. So once I go through those basics, I'll then discuss their similarities and differences, because the hype right now is artificial intelligence is great, it's out there, it's faster. Well, there are some distinct differences that need to be highlighted about that. And then I'll talk about the use of AI-based forecast against numerical weather prediction-based forecast for decision-making, and then wrap it up with some concluding remarks. So jumping right into it, we're going to review numerical weather prediction. So I'm going to abbreviate that going forward as NWP. And I'm just going to introduce everyone to the foundation of NWP. So what are the models made of, how they are initialized, why they take so long to actually generate a forecast. So our numerical weather prediction forecasts are actually initiated from weather data that we observe all over the globe. We have balloon soundings that go up globally twice a day around the world. We have surface observation stations. We have thousands of satellites in our upper atmosphere. So we use all of this to get information about temperature, pressure, dew point, actual ambient temperature in the atmosphere, and humidity profiles. From that, we can really start to figure out what's going on within the atmosphere. And so we feed that into numerical weather prediction models, and we use that as a base state or our model initialization forecast. Another item people don't recognize for observations are aircrafts. Our airplanes actually have sensors out there that collect information and transmit them back to recording stations at the surface, and we can use that for real-time updates into our initialization of forecast models. So then we have this data, we initialize it, and then the forecast is generated. So how is this generated? Numerical weather prediction, the ultimate goal is to predict changes in energy, mass, and momentum within the atmosphere that generate weather. So there are actually fundamental equations, they're dynamic equations, differential equations that represent this fluid motion that happens in the atmosphere and captures all the energy and moisture fluxes that go on. So we utilize the thermodynamic energy equation, ideal gas law, conservation of mass, Reynolds equations of motion. So we look at wind not just in the vertical and horizontal, but then in the third dimension, the Z dimension, and then we also look at it through time, right? And then we look at the conservation of moisture. So our global climate system and then our subsystems where we experience weather, we conceptualize and account for that all being continuous. So it's in balance, and we just have the energy, mass, and momentum that is being redistributed within the system. So numerical weather prediction takes that into account. So then as the model is initialized, equations are solved within each cube. As you can see in the picture here, it's a three-dimensional cube that goes up through varying levels of the atmosphere. And then each of these equations is solved, and the result is exchanged to the cube next to it, right? So then it's totally mapping out the entire response of the atmosphere within numerical weather prediction models. So in addition to those fundamental equations, we have what are called parameterization schemes. So these parameterization schemes are additional equations that are actually modeling smaller scale processes that also exchange energy, mass, and momentum within the atmosphere. So we're talking about smaller interactions like convection. So we have models within NWP that just focus on cloud development. We have land surface interactions, so your moisture and heat fluxes between the ground surface into the overlying boundary layer. Radiation, that solely focuses on radiation coming into the atmosphere from the sun down to the surface. So we have all of these smaller parameterization schemes that are going on within the model, and then we have the parent model that's being driven by our fundamental equations. So it gets very complex very, very quickly. So again, these are coupled equations. So this is happening on all our grid scales across space and time. And the key point here is not only do they capture what's happening here and now, they approach this from a chaotic and stochastic behavior. So a stochastic and chaotic modeling approach. And that's going to be important to remember for later on in our presentation. Artificial intelligence. Let's look at how AI models initiate weather forecasts or have come about to develop weather forecasts. So typically the building of an AI model begins with reanalysis data sets. This isn't always the case, but reanalysis data sets are kind of the big go-to data set to start building our models. So what is reanalysis data? This is numerical weather prediction, NWP generated gridded weather data sets. So that's key number one there. It's NWP generated weather data sets, okay, that we're using to train our AI models. But reanalysis in and of itself is a blend of historic weather observations, again, from the same data platforms that we're initializing NWP from. Aircraft, satellite, surface observation networks, weather buoys, ship buoys. The only difference with reanalysis is that we're taking a model, we're taking historically observed data, and we're initiating that model at a time that's occurred previously. So it's kind of hindcasting, right? So instead of it predicting a future forecast, we're taking a model and we're initializing it with past data, and then we're getting an output that is representative of how the atmosphere unfolded historically. So that's how reanalysis works. So with that, we then can have a gridded data set of weather and climate that has unfolded, as in this picture here, from the turn of the century to present day. So then by utilizing this reanalysis, we feed this into AI models, and AI models look at this through time, and they analyze the output through each time set, and they learn, or they pick up on behaviors or patterns that are changing between each image, and they're remembering this. So they're remembering how the changes are happening and what points are connecting where. And this is commonly achieved through deep learning and artificial neural networks. So these artificial neural networks function pretty much just like the human brain. So if you have ever gone through the exercise where you're having a conversation with somebody, and then you're like, wait, how did we get to this point in conversation? And you start thinking back of the different points in your conversation that led up to that point, your brain is basically making connections through its own neurons, right? And establishing a connective path. So neural networks are set up the same way in artificial intelligence. They're looking for behaviors to connect points to predict future states. So breaking this down pretty simply, with reanalysis, I just want, the users or the viewers who utilize this data to think of it as a simple exercise that I'm going to show here. We take an output file of a specified variable. For instance, this is the INSEP in North American Regional Reanalysis. It's our 100 millibar height composite mean. So this is our specified variable. And each pixel within that gridded output is assigned a value by the AI. And then that pixel is identified by that value. And then the AI model is going to look for pixels, all of that same value, and it's going to group them together. It's going to categorize or classify them. The next point is introducing the next time step. So here I have the 6Z, and the next time step is the 12Z. So it's a 6-hour difference, but that's the resolution of NAR, which is short for North American Regional Reanalysis. So we're presenting in a second image, and basically AI is going to take the difference between the two. So the graphic that I have just pulled up here, difference between T naught, which represents our first image, 6Z, and then T naught plus 1, T naught plus 1 being our second image. This is basically the difference between the two. So then the AI model is going to look at this image and try and determine, okay, what changed and how did it change? Is there a pattern to how it changed? And then we do this. We repeat this thousands and thousands and thousands of iterations with AI models. We feed them time step after time step after time step, and they repeat this process. And as we go through time, it trains itself to start recognizing these behaviors and patterns that are unfolding for the specified variable that it is reviewing. And then as this goes through the entire time series of the specified variables, it basically develops this predictive behavioral forecast pattern to create its own outlook for a future state based on all the input files it has just analyzed. So specific to artificial intelligence and weather forecasting, there's two types of applications that really hone in on weather applications. We have our reactive machines. Those have no memory and they focus on one task. So they take input data, generate an output data set. Basic learning, supervised training. So what do we mean here by supervised training? There's unsupervised training and there's supervised training. Basically, supervised training is when a human being interacts with the AI model to help train it and help it understand the data it's looking at. When a model is unsupervised, there's no human interaction with that model, and that model is basically training itself based on the data it's seeing and the data it is analyzing. The next type of memory is limited memory machines. So this is the next level of AI. It can investigate the past, focus on specific objects, and then start ingesting that data and training itself from it. So this is where we start to see the artificial neural networks and deep learning type of AI come into weather prediction forecasting. So with that basic introduction, how about we review the similarities and the differences between the two? So I'm just kind of bringing everything back together to highlight these key points. That way we can move on to the next steps and kind of build this foundational relationship of how they are similar, how they are different, and what this means in use and application. Similarities. Both approaches ingest observational weather data into the model. Both use equations to forecast an outcome, but these equations are fundamentally different. So that is a very important thing to remember. Both do produce images or graphics for a forecast outlook, and both models are actually fairly accurate in the short term. But if you remember, I said a lot of these models, these AI-based models, are trained and developed from reanalysis data sets that are actually produced from numerical weather prediction. So if you're utilizing numerical weather prediction models that have strong forecast accuracy in the short term, it's inherently going to manifest or show up within the output of the AI model. Now, differences, again, back to the equations. We have the governing equations of atmospheric motion and processes that are surface and subsurface that are driving these models, whereas the equations that drive AI are not founded on those relationships. They're a different algorithm that develops every time that you retrain a data set. Artificial intelligence requires NWP output. So NWP output can initialize on its own and create a forecast, but without NWP, we would have a much more difficult time developing AI forecast models as they are today. NWP is computationally more expensive, so it takes significantly longer to produce a forecast, which a lot of people can, find troubling, because if we're having a severe weather outbreak event and we're only getting 6-hour forecast updates from our models, and severe weather happens in a matter of minutes to hours, we need a model that outputs results faster. AI compared to NWP is substantially faster. Another difference is that NWP uncertainty can be quantified, which is very important, especially to a forecaster, where AI uncertainty cannot yet be quantified, or it's not fully conceptualized how we can quantify forecast uncertainty within these models. AI can be retrained with more recent weather data, so that does provide the premise or the understanding that if we're retraining with more recent observed reanalysis data sets, we're better capturing, or could be better capturing, the warming signal that we're currently seeing and experiencing in the global climate system. With numerical weather prediction, to make that shift, there's a lot of research and adjustments that have to go into the fundamental equations and parameterization schemes to get them to represent a warming climatic state. NWP can also forecast more atmospheric variables through time. So it does provide better insight to what's going on in the atmosphere versus AI, but that doesn't mean that one is better than the other. Again, these are key differences, and it's going to come down to the end user as to what they feel is most valuable to them at the time. So moving to the next step, using and applying AI to NWP, or AI and NWP to decision making, I think the key questions that are out there among the community is: what is more realistic? What is more accurate? What is more reliable? Well, it's not so straightforward, right? And I think that's why we're having this discussion today. But to understand the answers to these questions, or at least how I'm going to try to answer these questions, I want to dive into weather data just a little bit, and I think it'll help set off some of those light bulbs to understand why this is a hot topic, and probably will continue to be a hot topic with months and years to come, right? So characteristics of weather data. This is where we get into the statistics and the data distribution. So the meat and potatoes, which I like, but not everybody else does. But many weather variables follow a normal Gaussian distribution. So that's your typical bell curve. And that makes this data much easier to predict, right? A lot of this is temperature, seasonal rainfall. And with that, we have that data globally. That exists globally. We have sufficient data to capture that, say, within our reanalysis data sets. Now, there's other type of weather phenomena, which is more our subscale processes that our NWP parameterization schemes capture rather well, in the short term at least, are other variables that are not normally distributed through time. So this data is best captured in what we call Poisson distribution, and this is convective rainfall events, typhoons, hurricanes, tornadoes, right, are big drastic events. So those are more difficult, more complex atmospheric phenomena. So this in turn starts to create some issues as we jump or move into the AI side of weather forecasting. So thinking back to NWP, numerical weather prediction uses the fundamental atmospheric equations to create its forecast. These equations, as I've said, are very complex, and these equations basically forecast deterministic, chaotic, and stochastic systems. What does that mean? So let's break this down, especially compared to AI. What does this mean to AI? And I hope to kind of show you what it means so that we can make better decisions with this information in the future. So if we are looking at deterministic systems, this is based on precise inputs and outputs, right? So this goes back to the normally distributed data sets, our Gaussian distribution. So our temperature profiles, seasonal characteristics of a point at a latitude and longitude point. I use Dallas here as an example. So compared to AI, well, I shouldn't say compared to AI, but how does AI hold up with that? AI doesn't really struggle with this. It's easy for AI to determine deterministic variables or atmospheric states, right? It recognizes the pattern easily, and it can easily predict it at future steps. But now if we're looking at our chaotic systems, so chaotic systems are deterministic in nature, input results in an output, but there is sensitivity to the output based on the initial condition. To try and conceptualize this, I provided the picture here. So there are 4 different maps or graphics that you see with different names and numbers at the top. And what I'm showing is the mean distribution of extratropical cyclones in the northern hemisphere over the continental United States. But in each graphic, it's been generated utilizing a different reanalysis data set. Okay, so I tweaked the initial condition for the model that this went into. And you can see each of these resulted in a different forecast, a different mean of cyclone per grid square. So that is how I want you to conceptualize chaotic, right? So our chaotic systems are these more extreme systems like extratropical cyclones. There is sensitivity to that initial state. How does AI handle this? Basically, it recognizes these general patterns with the deep neural networks that I've highlighted in this conversation, and if we provide the sufficient training data. So AI handles pattern changes relatively well. Moving on to the most difficult type of system to model, the stochastic system. So the initial input state can result in a variety of outcomes. So that actually is where AI is more likely to struggle in terms of weather prediction. So it might forecast a hurricane, and it might do well with the track, but the pressure gradient or the low pressure center of that hurricane, the difference across the millibars to show that pressure gradient might be minuscule. It might only show a 5 millibar drop in pressure, when in reality, it's significantly greater than that. So we're still seeing AI struggle with some of these more stochastic systems and model prediction. So for decision making, which is a more realistic modeling approach to capturing atmospheric behavior, at this time, numerical weather prediction, right? It uses the fundamental equations that's built on physics and fluid dynamics and motion and the deterministic, chaotic, and stochastic systems. Which is more accurate? So this is kind of the hot topic right now because AI is showing promise. Well, both have similar forecast skills in the short term. And again, this goes back to the point that I was stressing that if we are training AI models from NWP forecasts, then those AI output are inherently going to have similarities or similar accuracies to what we see from the original NWP model, right? Which is more reliable? Right now, numerical weather prediction or conventional forecast models lend itself to a stronger reliability because we can quantify this uncertainty. We know what equations are driving those models, so we can go back and we can figure out why a forecast resulted in what we saw. So we can figure out from forecast told me this would happen, we saw this happen, we can go back into that model and figure out where that path diverged. When we can't do this with AI. We can't do it easily because again, every time we feed an AI model new training data, it changes its forecast approach. So if we have a model that's constantly changing its forecast approach, we can't gauge its uncertainty, so there's lower confidence there, especially within the forecast community. So the one key point I really wanted to hit home here too is, why are we suddenly seeing the surge of AI prediction in weather? Well, a lot of this is due to the advent of reanalysis data sets. They've really started to come mainstream within the last 10 to 20 years. And that's because with the advent of the satellite era in the 70s, 80s, and 90s, when we started getting all these remotely sensed platforms in space, we started bringing in a wealth of atmospheric information. And then we were able to learn and get that incorporated into numerical weather prediction models. So we now have these data sets, 30 years of robust data sets that we can now use to train AI with sufficient data to have a realistic model develop, right? So I think that's really why we're starting to see AI come to life, is just because we finally have the data available to start seeing and applying this to weather prediction. So the European Center for Weather Research here, they've recently published or put out to the public some of these AI-based forecasts, right, that are using their reanalysis data set. And there's been some questions, you know, are agencies in the US doing this? Are other countries doing this? I like to tell people, well, AI has actually been around for decades, and globally within the meteorological community. It started back in the 90s, right? It's just it's been developing, and we had smaller data sets, you know, 10, 15 years ago. So we didn't have a full grasp on how AI would unfold and apply to weather prediction in the future. And then again, not being able to quantify that uncertainty has made it difficult for meteorologists to vet that against the output of conventional forecast models. Quantifying uncertainty within a forecast is very important to the decision-making process of a meteorologist like myself. I need to understand the base state of the model, how it's bringing the data in and coming up with the forecast it's putting out. If I can't understand that and take that into account in the forecast I'm making, then to me, the forecast that I'm looking at is useless, right? So with this, that's why AI weather forecasts have not been provided to the public until more recently. There was still a lot of research to be done, a lot of understanding to be had in this process, but now that we have these reanalysis data sets available, we're starting to see the applications roll out more quickly in the coming years. But at this time, my consensus is we should be using these AI-based forecasts in conjunction with NWP. And again, that's mainly based on that uncertainty that we can't really quantify right now with the AI-based forecasts. So wrapping all this up with some conclusions, as I've shown, numerical weather prediction and AI weather forecasts, they have similarities. Their approaches are similar, I should say, but they're also distinctly different. And again, the key component here is we can quantify uncertainty with NWP, so we tend to have more support, or not more support, we have more confidence in the output of those models compared to artificially intelligence produced weather forecast. NWP, because it helps recreate our reanalysis data sets that train forecast models, it means that our AI-based forecasts are going to have some of the same similarities in output, or accuracies, I should say, as our NWP models. So right now, as we're seeing, AI is predicting as well in the short term as some of our conventional models. But again, if we're training AI on the output of conventional models, we're going to see our conventional model forecast accuracy manifest in the AI output. NWP does have a stronger grasp on atmospheric phenomena, spanning the different spatial and temporal scales. And again, that's because those fundamental equations capture the deterministic, chaotic, and stochastic behaviors, and AI has not quite gotten up to par on how to model, especially the stochastic behaviors. So until we see that align, we're still going to see differences in forecast accuracy, especially in those more extreme type of events. While AI is computationally less demanding and shows forecastability in basic parameter forecasting, such as temperature changes or general pattern changes, it still is showing these weaknesses that I've discussed and highlighted here in this conversation. So really, in the end, I hope with this presentation, I've provided some insight into the different approaches of conventional weather forecasting versus AI-based weather forecast, how they're similar, how they're different, kind of the key outliers here, the key components that we really need to remember regarding the differences between these forecasts, and really recognize that until we can fully vet uncertainty with AI-based weather forecasts, we need to use both of these products together. So use AI as a tool in conjunction with NWP.
Olivia, that was actually amazing. I learned so much. Because AI is coming along and is machine learning, obviously it'll keep getting better and better with time, right?
Yeah.
It's the way or the beast that we have. Is there any chance that from a longer term perspective on patterns, it could give us better pattern recognition down the road? I guess I'm asking that question because, one of the things we in the world of crops and animals and agriculture deal with is can we get, we're very good with the models going out 10 days, but we're always looking for that edge going forward. What would you say
Right.
to any of that?
I think there is promise. Yeah, that AI will get better and better as more of the research community within meteorology and climatology start utilizing and applying AI in research and applications. We're slowly going to enhance AI's capabilities to better pick up on those signal changes or pattern changes within the atmosphere. Um, so that being said, if I have a medium range forecast from NWP that says my pattern's not going to change, but AI shows a pattern change for the same time frame, I would use them in conjunction with each other. And I'm not going to lie, I'd be biased towards the forecast model, but that's because I know more about the forecast model and I can quantify that uncertainty. But that's not to say that AI is going to be wrong. It may be recognizing something that the forecast model has not picked up on, and it may prove right. But I think the more time we have analyzing these two approaches and seeing how they pan out and verify in real time, the better AI will become. And it could potentially become a very, very strong tool in the future, especially for pattern changes and longer range forecasts.
Yeah, yeah. I just want to make sure that the tools in our box, we understand them. And if you wouldn't mind, I'd love to have you back in 6 months or a year just to keep us abreast of, which model is gaining and where we're looking. And so we in the industry of agriculture understand, the balancing act that we should look at each of them. And I say this, I hate to be a guy that tries to be a weatherman, but we all in agriculture try to be weather people. And
Yeah.
and again, we'd like to be in your seat because what you bring to this business is tremendous. So my thanks to you for this presentation. I know we're going to be talking again. Climate Impact with Scott does a great, run every day, but I really appreciate this deep dive into AI versus the numeric models. And I think for me, it just put it in position of trying to understand where we're at. But I believe this is something that'll be changing quickly as we think about 6 months and years from now and how this will all play out as machine learning really maybe has a little advantage, I hope, going forward.
Yeah. Yeah. Well, thanks for having me. I'm glad, I could provide a little more insight on this. And yeah, I'd love to come back 6 months to a year and revisit. It never hurts to keep up with the most recent research that's coming out and applications to industry. So that sounds wonderful.
Thank you, Dr. Kellner. We really
Yep.
appreciate being with you. Wonderful presentation. We'll
Thank you.
miss you at GrainCom this year, but hope to have you back again soon. And again, just great information. Thank you, Olivia.
All right. Yep. You're welcome. Thanks for having me.